Thermochemistry. The oxidation of copper 1 oxide to copper 2 oxide is an exothermic process. Exothermic means releases heat, so it has to be negative heat. Calculate the energy released as heat when 46.56 grams of copper 1 oxide undergoes oxidation at constant pressure. So we're given 46.56 grams of copper 2 oxide, and we want energy released as heat. So we want kilojoules by itself. So I know that I'm given the heat of vaporization in kilojoules per mole of whichever substance of the reactants or products it's looking at. So I want just kilojoules. I need to get rid of the mole. So I'm looking at copper 2 oxide in the heat, which means that I have negative 292 kilojoules released per 2 moles of copper 1 oxide. Since that negative 292 has to do for the entire reaction, it could also be negative 292 per 1 mole of oxygen or 4 moles of copper 2 oxide. But we're looking for the release, meaning we have to have that negative sign of heat for kilojoules per copper 1 oxide where the 2 moles comes from. So I know that that's kind of where I have to end, which means that I have to get rid of moles. Since I'm given grams, I have to go to moles to then cancel out the moles. And the only way I can go from grams to moles is molar mass. And then I can go to heat using the enthalpy of vaporization. So it's kind of my steps. So 46.56 grams copper 1 oxide times, I want to get rid of grams and I want moles, so I have to look up and calculate the enthalpy, the molar mass for copper 1 oxide, 143.9. 1 mole goes on the top, 143.09 grams goes on the bottom, so then grams cancel, and then because you want heat release, negative 292 kilojoules per 2 moles of copper 2 oxide. Moles cancel, you're left with heat, which is exactly what you wanted. So then you just plug everything in. 46.56 divided by 143.09 times negative 292 divided by 2. So negative 47.5, we want 4 significant figures. So negative 47.51 is the answer. So for thermochemistry, the important thing to note is you're always given some kind of a heat, some kind of enthalpy, like this. And that pertains to the amount of heat either absorbed or released per mole of every single reactant or product. This could have been 292 kilojoules per 1 mole of O2. Since there's no coefficient, there's always 1. Or 292 kilojoules per 4 moles of copper 2 oxide. So it's always per mole of the reactant and the product. And then depending on what you're given, you just try to get the unit you're given to moles so that your moles can cancel and you are left with heat. Now, one more important thing to know is if you're asking for a heat released or absorbed. We left it negative because we're thinking of an exothermic process, heat released. If it would have been positive, we would have had to just